Hello everyone, Oleg is here. I'm going to refresh some calculus knowledge using this book, and I decided to share some thoughts on it. The topic of today's video is to define a function and look at some examples of it. The plan, you can see this on the right, so we'll start from the definition of a set, then we'll define a function. We'll talk about what is a dependent and independent variable, and then we'll define several ways to define a function. We'll talk about several ways to define a function. So we'll start with a set. So let me take my tablet. So a set is a mathematical entity which contains several elements, and to be specific, this is a collection of distinct elements, so none of the elements may happen more than once. And a set is defined within curly brackets and depicts all the values inside. So set may contain, for example, whole numbers. Set may be an empty set, and the set you all are familiar with is a set of natural numbers, which starts from 1 and covers each whole number and goes to infinity and beyond. So this is a set of natural numbers. So now we can define a function. So we know what the set is, and we need two sets. So the first set will be x capital. I think it's from Greek. So this is a set of some values, for example 1, 2, 3, and we have another set y with another values like 4, 5, 6. So these are two sets. And finally, the function is a mapping of set x to set y. So in other words, this is just some law to say how each element from x is mapped to each element of y. This is very important to highlight that each x is related to exactly one y. So this is an example of our function, which maps each value from x, 1 to the other value of the corresponding value of y, 1 to 4, 2 to 5, 3 to 6. So this is the simplest definition of a function, is to map some dependency or some logic. The other way to define is to show a set which will contain pairs from both sets. So the first one goes from x and the second one goes from y. So the first pair is 1, 4, the second one is 2, 5, the third one is 3, 6. So this is also a function, like a definition of what the function is, like an ordered set of pairs. So now we know how to define a function. This may be very important in some papers, for example, which define functions in various ways, for example through sets, which is sometimes complicated and not something we have seen at school. Now we know what the function is, and it's important to highlight what here is dependent and what is independent. And if we talk about x, we can vary it however we want. For example, we can pick any value from the set given. We can take 1, we can take 2, we can take 3 easily. But talking about y, we cannot do the same. For example, if x is 1, if x is already taken as 1, we cannot take any random y. So the only one we can take is 4, because there is some dependency linking x and y. And basically this defines the dependent and independent variables. So all x are independent, we can vary them however we want, while y's are dependent. In other words, we can just say that when we vary x, y changes. So y is dependent. The next thing we're going to cover ways to define a function. So there are actually 3 ways: analytical, tabular, and graphical. So here they are. I will start from the first one, analytical. Analytical way of defining a function requires some explicit formula. For example, we can say that y of x means that just y is the the name of an element from y. So this is a notation to say that y is some element from y, and of x, brackets x, parenthesis x, means that this is the value at some point x. For example, there may be some function x plus 1. So this is just some analytical definition of the function y. We can name it differently. We can name it, for example, f of x. It doesn't matter at all. So we can say that this is, I don't know, x squared. So for each x, we have some corresponding f through this law. So for example, for x equals 2, f will be 4. So this is the analytical way to define a function. We need some explicit formula to do that. The second option is tabular. This may be depicted as following. So we have some x and some f of x, and we have some table of values. So for example, for xy, we have the value of x2, for x2 we have the value of f3, for 3 we have 4. Why this is interesting? Because in some cases we do not know the exact law which links f and x, or y and x, however we call it. Again, this completely doesn't matter. So we do not know the law, but we know some examples. And this is, for example, a very usual case in machine learning, when you know some examples of x and y, but you do not know the law, the exact law which links them together, and your goal is to approximate and find this law. Another important thing to highlight is that, for example, you are given this table, and there is a very simple idea and wish to extrapolate this function. So you can guess, for example, that the value at the point 4 will be 5 and so on, because you see a simple linear linear dependency between these two rows. But this is kind of impossible at this stage because the value of the function here may be completely random. So this is not defined here. You can deal only with the values, certainly can deal only with the values which are given, and others are kind of not defined and they may be only approximated. So the tabular way of definition is covered, and the last one remains is graphical. So you may guess why do we need this way of defining a function? So this is f of x, this is x. Why do we need to draw something? Why don't we just write some analytical law of it, or analytical formula of it? The answer to that is because not all the functions are easily definable in formulas. For example, this join or image I have shared, even looking quite simple, may not be easily depictable as a formula. So for example, this may be equal to some very, very complex large formula, so that's why it is not always simple. The other reason for that is that not always we need the explicit formula of the function. For example, let's say that we're looking at the electrocardiogram, which looks like the following or something similar. And a doctor, a specialist, doesn't need the formula, the exact formula of this law or dependency, because it's already enough to deal with the image or with the graphical representation of the function of the dependency, which will be, I think, time and some stimulus or some intensity of your heartbeat or whatever. So this is the reason why graphical option also exists. Another idea or example may be seismograph, which depicts some deviation of the needle on the paper depending on the earthquake activity at the moment. So this may be another thing which is then translated to some Richter scale, and you can say, I don't remember how his name is written properly, but something like that. So then this scale is translated into the Richter scale, and then you can say what is the intensity of the earthquake. So this is it. Today we covered the definition of the function of a set and the concept of dependent and independent variables and different ways to define functions. This is very important to start simple and understand the basics of function definitions, to understand difficult scientific papers and difficult methods of dealing with these functions, and I hope I will cover them soon. Thank you for watching.